So first and foremost, welcome to Fundamentals of Chemistry. Okay, so my name is Saoirse. I'm going to be your lecturer for this semester, and I'm going to take you through the Fundamentals of Chemistry module. What I would say is that this course is going to provide a very kind of high-level brief overview of chemistry, and it's more to set you up for your modules that you will take in year two, centered around your kind of manufacturing process and your introduction to pharmaceutical science. Okay. So what I would say from the outset is don't stress. It's not going to be like real in-depth chemical analysis or anything like that. We're just going to give you kind of a brief overview of some of the theory behind chemistry, more of the calculations that you'll use in the lab, and then some of the kind of key concepts that you'll need for those calculations. Okay. So first things first, I'm going to start sharing my screen then, if you just want to let me know if you can see this okay. Can everyone see that okay?
Yeah.
Yeah.
Okay, perfect. So that should be in slide view now. Okay. So I suppose before we get started into the theory of it, I'll just go over a couple of quick notes of how these online lectures are going to be run. Okay, so you may have seen my previous email that the lecture schedule has been posted to Moodle. Okay, so this will kind of consist of 2 week blocks that are online mixed in with some 1 week blocks that are actually on campus at SETU. So that's posted online at the moment. There is one 3 week block that happens after reading week, but we'll get to that once it comes, okay? So that's there for your review. So what I will try and do most weeks is that, similar to what I did yesterday, I will try and post the lecture material on by Sunday evenings. Okay, so that'll kind of give you a chance to look over any of the material that we're going to cover. If you have any questions then for the lecture, it will kind of make it a little bit easier just to review during our Monday evening lectures. Okay. So the one thing I do want to talk to you about is the lectures. I'm planning to record them. Okay, so that it's just in case that if any of your work schedules change, that you will have access to the lecture material afterwards. The way I'm planning to do this is to upload them to a private YouTube channel. Okay, so I will share that link after this class that only this class has access to. So then you'll have maybe about a week once I upload the material to the YouTube channel to kind of review it, and then it will be taken down. I did put up a GDPR consent form on Moodle. So if you do not wish to be recorded or you don't want your name or face in the video, that's no problem at all. Just let me know and then I can edit it out before I put it up online. But just so you know that they will be only available for a week and then they'll be removed. Is that okay with everyone?
Yeah.
So far anyway? Okay, perfect. So I suppose the next kind of big thing that we have to organize are the Saturday lab practicals. Okay, so in the Fundamentals of Chemistry course, we have 2 Saturday lab practicals. Okay, so these are from 9 a.m. to 5 p.m. and we cover 8 fundamental lab experiments in this. So once we kind of organize the dates, I'll go through what experiments we're actually going to cover. The only thing is these lab practicals are mandatory. Okay, so I'm kind of hoping that we can decide on the dates this evening so we can lock them in, and then if anything changes them, you can let me know in advance. So I suppose in terms of when I was thinking, I'm not going to start them until October. And I was thinking we could do maybe the 10th of October. So the Saturday, the 10th of October. Oh, sorry, is that Friday? Sorry, no, the 11th of October. Sorry, Saturday, the 11th of October. And then maybe November the 1st. How does that work for people?
That's fine for me anyway.
I'm actually away on the 11th, Saoirse.
The 11th of October, okay. Let me see now. That's no problem. Just give me 2 seconds and we'll have a look at it. So how about we do the 18th of October and the 1st of November? Would that work?
It's okay for me.
Yep.
Yeah. Okay, perfect. So what I'll do is I'll put those into the schedule as the 18th of October and the 1st of November from 9 until 5. And look, if anything changes in the meantime, we can take a look at it then. Just as long as we get them done before the end of the semester, that's all that matters. Okay? Perfect. So does anyone have any questions on that before I kind of delve into the material?
Hi. Sorry, I should have spoken up. I'm actually away the weekend of the 1st of November, but I don't want to ruin your plans like for one person, if you know what I mean.
The 1st of November. No, that's right. That's what we're talking about now, so we can kind of nail down a couple of dates that suits everybody. So just to recap, everyone's okay for what did we say, the 18th of October? If we could
In
do
October, yeah.
so the 18th of October. So what's everyone's availability then? Maybe we could do one after the other. So that means that we have 2 Saturdays in a row, but at least all the experiments are done well in advance of the semester deadline. Would that work for people?
Yeah, it's okay.
You okay with me? Yeah.
Perfect. Okay, so yeah, so we'll do the 18th then, and we'll say the 25th of October. So that means we have everything done well in advance of the lecture deadline, and then we have time then to kind of do more tutorials towards the end.
Yeah.
Perfect. Okay. So what we'll do is then we'll get started with our lecture material. So has that moved on for people? Can everyone see the fundamentals of chemistry slide?
Yeah.
Perfect. Okay, so like I was saying at the beginning, okay, so this course is designed to kind of give you a very broad, well-rounded view of chemistry, okay? We're going to take it from the very beginning, so you don't need to have any chemistry background for this. It's a bonus if you do, but you don't need it. We're going to basically look at the kind of why we study chemistry, where do the concepts come from, how those concepts feed into what we actually do in the lab, and then we'll tie into the kind of the modules that I mentioned earlier, like your manufacturing and processing and your introduction to pharmaceutical science. So how it all ties in together. Okay, so I suppose starting at the very, very beginning, what is chemistry? Okay, so it's the study of matter. So matter is anything on Earth that takes up space and has a mass. So if we can see it, if we can hold it, we can weigh it, that's matter. We're going to delve in a little bit deeper then into what matter is. So we're looking at its components, or what we call the building blocks of matter, and its properties. From there then, we look at those small building blocks, their properties, and how they interact with each other based on these properties. So this is kind of tying into how 2 different building blocks or the components bind together to form new substances. Okay? So from there then, we have our building blocks. We know how they interact with each other. And then we look at how we can manipulate those interactions through reaction conditions in order to produce a new product. Okay? So I suppose to give you a brief definition of matter, matter is any substance that takes up a region in space and has mass. So this is anything on Earth. The one thing about matter is that it can't be created or destroyed. So even though we are going to be producing new products, they don't form out of thin air, okay? We take starting materials or our chemicals and we convert them into another form through chemical and physical changes, okay? So we can never create new matter. We're not playing God. We're just taking starting materials, looking at the interactions between them and how they form a new product, okay? So I suppose the simplest explanation of this is that if we were to look at water, okay, so we can see kind of different variations of water in this picture here, and that exists in 3 states. All right, so we have our ice, which is our solid, we have liquid water in the sea, and then the gas is our water vapor in the air, okay? So we can see that if we melt ice, it forms a liquid, okay? We don't destroy it, we don't create water, we have just simply taken ice in a certain form, put it through a physical change in order to form water. To turn it into a gas, then we then take that liquid, put it into another physical change in order to form gas. Okay, so as you can see, it doesn't disappear, we don't get rid of it, we just simply turn it from one form to another.
Sorry, Fierce, are you on slide 3?
Sorry, what was that?
Are you on slide 3? You know,
Yes, I'm on the fundamentals of chemistry, yeah.
Okay, I can only see the first one. I don't know whether anybody else has moved on, but my one
The
is on its
same.
own.
It's just the first one. We
First
can
one.
see.
Oh, sorry. Okay, so I thought it's on my screen here. Sorry, just give me 2 seconds and I'll try and fix that. Sorry about that. Okay, bear with me 2 seconds. Okay, can you see that now?
Yeah.
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 Perfect. Okay, so what I'll do is I'll just go back over that diagram there so you can just see what I was actually talking about, okay? So everyone can see the diagram of the ice and the sea, yeah. So what I was talking about, we have our ice, all right? So if we wanted to form the water, it goes through a physical change, okay? So we never actually get rid of the ice. We just convert it into another form, which is our liquid. But we never actually get rid of it, okay? The same if we wanted to turn that exact water into water vapor, we pass it through a physical change through heating, and that will turn into a vapor, okay? So we take water, we never get rid of it, we never use it up, but it just converts from one form to the other. And that is basically the fundamental principle of chemistry. All right, so we can take a substance, turn it into something else, but not create nor destroy it. Okay? Everyone okay with that so far? Okay, so if I were to talk then about the building blocks of matter, okay, so the best analogy I can come up with here are Lego bricks, okay? So the smallest building blocks of matter are called atoms, okay, so this is the smallest unit of matter. Atoms can't be divided into a simpler substance by any chemical or physical means. This is basically our starting point, okay? So if you can imagine, this is our little red Lego brick. If we wanted to build a whole Lego piece, we'd start off with individual bricks. These are our atoms. So if I were to say elements then, so we will come across this throughout the fundamentals of chemistry module. We'll be talking about the periodic table of elements. An element is basically another word to describe the type of atom. Okay, they're made up of only one type of atom. So if I were to show you these Lego bricks here, so we have a blue, yellow, and a red yellow brick or Lego brick, they are individual types of atoms. Okay, so an element is a pure substance that is only made up of one type of atom. It doesn't contain anything else but that atom. So essentially, if I were to take that red Lego brick there, split it in half, I'd only have red Lego bricks. Okay, so I don't have any other substance, it's just that. Okay, so then we move into what's called molecules. Okay, so molecules are how we describe a group of atoms. So if you could think of an element as one atom, molecules are a group of atoms, and then they can be further subdivided then. So molecules are made up of two or more atoms that are chemically bound to each other. So these are the interactions that I was talking about. All matter is made up of atoms and how they are chemically bonded together. Oh, sorry there. So if I were to show you an element, okay, we could have two or more of the same atom. Like I said, elements are pure substance. They only have one type of atom. And this would be a stack of blue Lego bricks. Okay, so that would be a molecule of that element. If I were to have two or more different atoms, that would be called a compound. So a molecule is basically a group. We have two subdivided into two others. A molecule of an element that has all the one type of atom. And a molecule that has two or more different atoms is called a compound. Okay, so as you can see there in the diagram, molecules and element would be a stack of the blue Lego bricks. Your molecules of a compound will be our yellow and our blue Lego brick chemically bound together. Okay, does anyone have any questions on that so far? Everyone good to go? Perfect, okay. Okay, so how this actually comes about then. So you may have seen this before as the periodic table of elements. Okay, so just a brief recap. Elements are pure substances that are made up of only one type of atom. So we have, and for this course, we'll only learn maybe up until element 20, okay, which is our calcium. So we'll be working back the way. So between 1 and 20 are the elements that we're concerned with here. So this is basically a good organization structure for elements, okay? So as you can see, they're organized in rows and in columns, okay? And what we have there, they're organized in accordance with increasing atomic number. So we'll get to that a little bit later on, but basically atomic number is the number of protons in the nucleus of an atom, okay? For now, all we need to know is that they're increasing atomic number, so you can see 1, 2, 3, 4, 5, 6, 7, 8, and so on. So basically, if I were to take one of these elements, and like I said about splitting the red Lego brick, if I were to split one of those in half, I would only have that element, okay? I'm not dealing with compounds here at all. We're only looking at the elements themselves. Okay, so you may notice then that these are organized by color. Okay, so the color represents the certain type of element that we have. Okay, so as you can see, we have alkali metals, we have halogens, and then we have our noble gases. Okay, so each one are in a group. So as you can see there, they're organized in our groups, and they all have similar chemical properties. So it's basically a very good way of organizing elements in one place. We have them by atomic number, and we also have them grouped by their chemical properties. Okay? So if I were to show you these, okay, so they're group 1, just as an example, are group 1 elements, okay? These are called our alkali metals. And what these are is that they're quite pliable metals, okay? So for example, these metals, they're called metals, but they can be cut with a knife, and they're also incredibly reactive with water. So these metals, for example, they react with water and they produce a metal, they call them metal hydroxides, but they also create hydrogen gas. So I'll show you an example of this. So we're going to look at potassium here. And just to show you an example of what I mean by reactivity. So can you guys see the YouTube video there?
Yeah.
Perfect, okay.
So what I have here is a piece of potassium metal. This is a metal like any other metal, but it's quite soft. You can see I can cut it with a knife. But potassium metal, like all metals that are in group 1 of the periodic table, that's down the left-hand side, are quite reactive with water. So imagine if you had some of this exposed in the laboratory and then there was a fire and the fireman came and threw water on it. Boom. Well, this bursts into flame because the reaction between potassium and water releases hydrogen. And then the hydrogen gas is what explodes.
Okay, so very brief overview there of what can happen when you drop potassium in water. Not recommended in a lab. But what essentially happened there is that our alkali metal reacted with water. It produced a lot of thermal energy. So it's very, very reactive. We'll get to why they're reactive in future lectures. And all of a sudden, that huge increase in thermal energy caused the hydrogen gas produced to react and essentially explode. Okay? So if I were to just jump back then to our lecture notes here. So all of these group 1 elements will react in the very same way. And actually the reactivity of them gets greater and greater as you go down the column or the group. So each one of these groups has different chemical properties is what I'm trying to say. Okay? So that was just an example. We'll mention a lot of the noble gases here on the right when we're talking about electronic configurations a little bit down the line, okay? Because these are incredibly stable. And we'll go into that once we reach electronic configuration. Is everyone okay with that so far? Perfect, okay. So we're going to just look back then on matter, okay? So I mentioned it briefly when I was talking about the water. So we had our ice, our liquid, and our gas, our water vapor. And we're going to look at the 3 states of matter here. So remember that I mentioned matter can't be created or destroyed. Okay, so we cannot pull material out of thin air, nor can we ever get rid of it completely. We can only look at converting matter from one form to another using chemical and physical processes. Okay, so this is where we talk about our reaction conditions, why we set certain pressures, why we set certain temperatures, why we carry out certain reactions in the dark versus under ultraviolet light. All of these contribute to how we change one substance into another. So looking at our 3 states of matter, okay, so we'll use our water as an example. If we were to look at ice, okay, ice is organized in a very rigid, solid arrangement, okay? So if we were to look down into the very atoms of ice, they are in fixed position. Okay, so those molecules of water that I was talking about, they are arranged in a very rigid fixed structure. The particles are very close together and they don't have a lot of free space to kind of move and flow around each other, hence why we have a solid structure. As you can imagine, if we were trying to compress an ice cube, it's very, very difficult because they're arranged in that rigid structure. Okay, so they're not very easily compressed. So if I were to take ice and I were to heat it, okay, so if I left it out on the counter or I left it near a radiator, for example, it would eventually turn back into liquid. Okay, so we would have water. As you notice, okay, water goes everywhere. If you spill it, it goes everywhere because particles now have the free range of movement. Okay, so they are still associated with each other. The molecules of water can still bind to each other, but they have a lot more room to move around. Okay, so they can flow past each other. Liquids, if you were to take that water and put it into, say, a beaker or a cup, the liquid would form or assume the shape of that cup. Okay, so solids have a very rigid structure. They will stand on their own. A liquid will take on the shape of whatever container it's in. But they do have a fixed volume. Okay, so we can take a liquid and measure its volume accurately using different methods like your graduated cylinder or your pipettes or burettes, but they assume the shape of the container that they're in. All right, so we still have, so we still have our interaction, but it's a lot less rigid and a lot more free flowing in a liquid in comparison to a solid. So if I were to take that liquid then, place it into a kettle, and then heat it to 100 degrees. Okay, so we all have kettles at home. I switch on the kettle. Eventually, over time, I'll see a lot of steam rising out of that kettle. I've essentially applied a lot of heat, and I've converted water in its liquid form into its gas or water vapor. Okay, so gas is kind of described as having like total chaos or total disorder. Okay, the particles have complete range of motion. They still do interact somewhat, but they're very, very far apart. So they can collide with each other, its surroundings. If we were to trap the gas into a container, it would collide with the surfaces of the container itself. And it has a lot of more empty space and a lot of free range of movement. Okay. Gases, they don't have a definitive shape. Okay. So if I were to trap a gas in a container, you wouldn't be able to see definite shape or a definite volume. All right. And if I were to work back the way, so if I were to take that gas, if you had the kettle on in a cold room and you were looking at the counter, you would eventually see if it hits a cold surface, it will convert back into a liquid via condensation. If I were to take the liquid then and put it back in the freezer, we have reformed our solid or our ice. Okay, so this is a great example to show you the three states of matter and how different physical changes can invoke different states of matter. Okay. Does anyone have any questions on that so far? No, good to go. Perfect. Okay, so now, like I said, we mentioned matter. Okay, we mentioned the three states of matter, and we've looked at certain physical and chemical changes that can happen to matter. What's important to know is that all matter possesses physical and chemical changes. Okay, so we'll go through both of these now. Your physical changes, so they can be absorbed without changing the substance into another substance. So this is going to be very important in your labs, or we're looking at certain material that we can take, or we can analyze physical properties without necessarily changing that substance into something else. So, for example, if I were to take say if I had ethanol and I wanted to see what the boiling point of ethanol was, I can boil ethanol up until its boiling point and turn it into a vapor, and I can measure the temperature at which that happens. Okay. If I wanted to reclaim or get that ethanol back, I would just take the ethanol vapor, condense it back down into my ethanol liquid. Okay, so I haven't changed anything. It's still ethanol. It's in a different state, but I can regenerate it by condensation. Okay. Melting points then. So again, you have, say, a sample of aspirin, for example, and you wanted to test its melting point, because melting point is a great analysis for purity. So if I had a sample of aspirin and wanted to test its purity, I would take a sample of aspirin, melt it to its designated melt temperature, and then record the temperature at which it melts. Okay. For example, then you have things like density, mass, and volume. So if I had if I was trying to weigh out sodium chloride in a lab, I would essentially place it onto the balance and record its weight. If I wanted to measure out a sample of hydrochloric acid, which is our liquid, I would pour a set volume into a graduated cylinder and then I can record its volume. Okay. The main point of a physical property is that the composition of the original substance that you start out with does not change. On the other hand, then, are chemical properties. So these can only be observed if a substance undergoes a chemical change into another substance. So there's kind of three main chemical properties here. So you have your flammability, your corrosiveness, and your reactivity with acidic substances. So your flammability would be if you wanted to test, say, for example, if you were burning wood in the stove, okay? You can only measure how much ash or carbon dioxide is produced from that reaction by deliberately burning it and reacting with oxygen in a closed environment, okay? So if I were to test the flammability of a wood sample, or I wanted to measure how much carbon dioxide was emitted from that, I would have to react it with oxygen, turn it into something else, or ash, so that it produces carbon dioxide, okay? Your corrosiveness then, so that's a big thing with, say, rusting on iron. If I wanted to see how much, if I left out a sample of iron outside and I want to see how long it would take for rust to form, I would have to deliberately allow iron to react with oxygen in the environment to form iron oxide or rust, and then I would be able to measure the time it took for that rust to form. But it has changed into another substance, okay? Your reactivity then, so I'm not sure if you've ever had experience with it, but like a related substances test in a pharmaceutical lab. So what would happen there is that we take a known drug product, for example. We want to see how stable it is under certain conditions. But to do that, we have to deliberately degrade it. Okay, so we have to leave it at very high temperatures. We have to leave it in the presence of a very corrosive acid, a very corrosive base, under certain light conditions, so that we can see what the potential degradation product is. But we can only form that degradation product once it reacts with under temperature or with that acidic substance or that basic substance. So all in all, we have to allow the composition of the original product to change in order to form a new product. Okay. So just the last slide on this particular lecture then. So we do have other types of properties that matter. So physical and chemical changes are the ones you're going to come across most. But we also have intensive or intrinsic, it might be called, or extensive or extrinsic properties of a substance. So intensive or intrinsic basically means that we don't need to know the amount of a substance that's there in order to analyze them. So if I had, for example, if I had 10 ml of ethanol or I had a liter of ethanol, the boiling point of that ethanol won't change. Okay, so I can do analysis on that 10 ml portion or that 1 liter portion, but the boiling point will always remain the same. The color analysis is a big one. So this is normally done in pharmaceutical companies to test kind of like based on your regulatory requirements, you'll have a color specification. If I had 1 tablet or I had 100 tablets, they should be the same color. So I can do that very, very easily without knowing how much of that material is there. Solubility is also another one. So again, doesn't matter how much I have. I can measure the solubility based on 5 grams of a product versus 10 grams of a product. Its solubility in certain solutions won't change based on how much is there. Okay. I suppose then on the other side of it then, the extensive properties are very dependent on the amount of substance that you have. Okay. So particularly mass. Okay. So if I had a small amount of a substance or a large amount of a substance, the mass is going to vary. Volume then is another one. So again, particularly with our liquid samples here, so I can measure out different variations or different amounts of our liquid, and they will obviously change based on how much I have. Energy then is another one. So the more mass or volume I have of a certain substance, the more energy it will emit during a reaction. So the more reactant I have, the more energy it will produce, and it should quantify in more product form then. Is that okay, everyone? Does anyone have any questions on that so far?
No, perfect, Saoirse, thanks.
Okay, perfect. So what I'll do now, so we're just coming up to 10 to 6 there. So what we'll do is I'll give you a 15-minute break. I will come back then and I'll do the second lecture that I put up. And then I just have a quick tutorial worksheet that will maybe take about 10 minutes to go through, just as a recap of what we covered. Does that sound okay to everyone?
Yeah, perfect, Saoirse,
Yeah,
thanks.
perfect.
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 Yeah.
So if we say we're back here then maybe by, we'll say 6 o'clock then, and we'll get started into the next lecture and we'll take it from there then.
Okay.
Okay, can you see the first slide there, yeah?
Yeah.
Yeah.
Perfect, okay. So we're going to take then what we learned in lecture 1, okay? So we've looked at the atom, we've looked at what elements are. So elements are basically pure substances that are only made up of one type of atom. So if I were to take an element, split it in multiple different ways, I'd only ever end up with the same type of atom, okay? We looked at what groups of atoms are. So we have 2 basically, okay? So these are called molecules. We could have molecules of an element, so they're all the one type of atom, or we can have a compound which has 2 or more different types of atoms, okay? So these kind of terminology is going to be important moving into when we discuss atomic and electronic structure. Okay, so the bit I hate the most is the history, but we do have to cover it, so I'm just going to do it very briefly. So we're going to look at where the actual theory of an atom came from, okay? So it was championed by this scientist called John Dalton, and he based this on 2 different laws, okay? So we have the law of conservation of mass. I've kind of touched on this already. It's basically that matter cannot be created nor destroyed. And we also have the law of constant composition. So to summarize his hypothesis, okay, so he took an element, so essentially our types of atoms, and he said that they were broken down into extremely small particles called atoms. Atoms are the simplest form of matter, okay? We can't take an atom and split it by a chemical means anyway. We can do it by nuclear reaction. We're not going to touch on that. Basically, what we know is that atoms, if we to alter that chemically, they are the simplest forms. We can't divide that any more than it already is. All atoms of a given element, so if I were to reference back to the periodic table, if we took maybe so we took hydrogen, or we took calcium, or we took aluminium, if I were to look at the atoms of that element, all of those atoms should be identical to one another in mass and other properties. So basically, if I were to take any one of those elements, take it apart atom by atom, all of those atoms should behave in the exact same way, have the exact same mass, and react in the exact same way under physical and chemical changes. Okay? Compounds, so what I mentioned, we can have 2 or more atoms that are bonded together, 2 different types of atoms. So for example, if I were to combine hydrogen and oxygen, I can form water. So water is a compound and has 2 different types of atoms. So we have that. And then chemical reactions then, so they involve the rearrangement of atoms. So again, we can't create atoms, we can't destroy atoms, we can just rearrange these atoms to form a new substance. Okay, so these were his 4 main hypotheses of his overall theory. So just taking a quick look then at the law of constant composition, okay? So what this basically means is that an elemental composition of a pure compound never varies. So if I were to take a solid gold bar, so our Au, the element Au is gold, if I were to take that apart, all of those atoms should be identical, okay? They will combine in a fixed proportion by mass, so that all samples of the compound are identical in composition by mass, okay? So what this basically means is that if I were to show you this reaction of water, all right? irrespective of the water source. Okay, so if I were to go to a river or to take a bottle of water out of the fridge, or I were to go to the tap, pure water will always contain hydrogen and oxygen in the atomic ratio of 2:1. So basically 2 hydrogen atoms will always combine with 1 oxygen atom to form water. Pure water anyway, okay? That will never change. If I were to take a sample of water from anywhere, those atoms should have, or those compounds of water should have 2 hydrogen atoms and 1 oxygen atom attached. That will never change. Is that okay with everyone so far? I can see where I'm getting that from.
Yep.
Perfect, okay. Okay, so the law of conservation of mass then. So I've touched on this briefly already. But what this basically means is that the total mass of substance that are present at the end of a chemical reaction, so if we have a set reaction, we react our starting materials to form our product, the mass of the product that we get at the end should equal the mass of the substances that we started off with before the process took place. Okay, so this ties into the theory that we're not creating any additional matter, we're not destroying any additional matter, we're simply converting that chemical substance from one form into another. So this reaction here, so I won't go too much into detail about this now, but we will come across this in our labs. When we react hydrochloric acid with sodium hydroxide, we're going to form water and salt from that. The reason I use this is, like, say, for example, we used 50 grams in total of hydrochloric acid and our sodium hydroxide. Even though we are converting both of these substances into a new form, so you'll see they're going to combine to form water and salt, we should end up with 50 grams of product in total. Okay, so that might be, we might end up with 10 grams of water and 40 grams of sodium chloride, but we still end up with 50 grams of total matter at the end. Okay, we're not taking it away and we're not creating something or additional products. Okay. Okay, so like I did mention that atoms can't be divided by chemical means. Okay, so if we were to split the atom, we would need nuclear physics. But we have to look at atoms under a microscope. Okay, and these are called the subatomic particles. So they all make up an atom, but the atom is made up of tinier subatomic particles. So this is a typical diagram of an atom. Okay, so we have what's called the nucleus, or the central nuclear region. All right, so this is in the center of an atom. Around the nucleus then we call these the electron cloud. Okay, so we have 3 main types of subatomic particles that are housed within this atom. Okay, so we'll go through these one by one. So the protons are found in the nucleus. So these are in the center of the atom, and so are the neutrons. Okay, so I'll go through what each one of these are in a second, but all you need to know for now is that protons and neutrons are in the nucleus of an atom. The electrons are found within the region of space surrounding the nucleus. Okay, so we call this the extranuclear region, but it's just the region of space around that nucleus. Okay, so for a little bit of a size comparison on how small these subatomic particles actually are, if I were to show you the nucleus of an atom and blow up its size to the size of an average blueberry, okay, the atom itself will be the size of an 80,000 seat capacity football stadium. Okay, so as you can imagine, if this were a blueberry, this whole atom is the size of a football stadium. Okay, so atoms contain a huge amount of empty space. In that empty space, these electrons are flying around in the shells or surrounding that nucleus. And in the dense nucleus, then we have our protons and our neutrons. Okay, so the way I tend to remember the names of these, it's called PEN, so protons, electrons, neutrons. All right. Everyone happy enough with that so far? Okay. Okay, so if I were to just show you then the common characteristics of these subatomic particles. Okay, so like I said, we have protons. These are in the nucleus in the center. Oh, sorry. nucleus in the center of our atom here. And these are positively charged. Okay, so we typically give these a charge of +1. And they weigh approximately 1 atomic mass unit. Okay, so they are tiny subatomic particles, but we give them a mass of 1 atomic mass unit, and they have an overall charge of +1. Okay, our neutrons then, so it's kind of in the name, they have no charge. Okay, so they're neutral, they don't possess a positive or a negative charge, but they also weigh 1 atomic mass unit, approximately. Our electrons then, so these are negatively charged. Okay, so as you can imagine, the protons and electrons are repelling each other within this nucleus here. So all our positively charged particles are in the center. Our electrons are flying around in the electron cloud within the shells or surrounding the atom, and they are all negatively charged. And then they don't have, we call it a negligible weight. Okay, so as you can imagine, this is a tiny weight. So we just say that they have effectively no mass. Okay, where this comes into play is that when we're looking at atomic masses and we're trying to figure out the actual mass of a compound, we're only looking at the masses of the protons and neutrons and not the electrons. We disregard that weight. Okay, so where this actually all comes into effect then. Okay, so if I were to revert your attention back then to the periodic table, you would have seen the element itself. Okay, so we normally label that with 1 or 2 letters. Some are different. So for example, gold actually has the chemical elemental symbol of Au, whereas silver has Ag, but most of the time they have the starting letter of their name. Okay, so for example, carbon is just a capital C. Okay, so we move on to atomic number then. So you'll see 2 numbers on the periodic table. Okay, so the lower one is called the atomic number. So this is the number of protons or electrons in an atom. Okay, all atoms, so again, you have your element. If I were to cut up that element, I would have all of the same atoms. And in each of those atoms, all of those atoms will have the same number of protons on their structure. Okay, and this is called the atomic number. So it's basically the number of protons in an atom. Okay, what's really important to know here, and we may touch on it kind of in future lectures, but for now, we're dealing with a neutral atom. Okay, so if you think about our positively charged protons, our negatively charged electrons balance each other out. Okay, so they basically have equal numbers of both. We don't have one charge over the other, and they cancel each other out. So we have a neutral atom. All right, we may come across ones that are called ions down the line that have a different charge, but we won't worry about that for now. So what we need to know for now is that all atoms of the same element have the same number of protons, and the number of protons is described by the atomic number on the periodic table. The mass number then above it, okay, so this is normally the bigger number of the 2, and this describes the actual number of protons plus neutrons. Okay, so the atomic number below is only protons, the mass number is your protons and your neutrons. And why this is important is because, going back to what I said here, is that both, sorry, this keeps jumping on me there. So the protons and the neutrons have an atomic weight associated with them, okay? So that's why they both contribute to the mass number. So your atomic number is only protons, your mass number, we have to take into account your protons plus your neutrons, because they both weigh the same amount, okay? Is everyone okay with that so far? Everyone can see where I'm getting those numbers from. All good? I haven't scared you off chemistry too much, no? Not yet. Okay. Okay, so just to kind of do a little bit more then. So if I were to show you this, so this is our carbon. Our mass number, number of protons plus neutrons, atomic number, number of protons at the bottom. We do have substances called isotopes. Okay, so we won't worry about these too much. I'm just going to touch on them briefly. So these are atoms of the same element that have the same number of protons. So again, they're the exact same atom. We were to cut those down onto microscope level and see each individual atom, they would have the same number of protons, but they would have different numbers of neutrons, which means they have different masses. Okay. The most common example here is our carbon isotope. Okay. So what we have here is that we have carbon-12 is our most abundant carbon element. Okay. Carbon basically mainly exists in nature, having our six protons and our 6 neutrons. It's most stable with this. Carbons, though, with a mass number of 11, 13, and 14, they do exist. They do exist in nature, but they're not as stable as our carbon-12 isotope. Okay. The only difference between each one of these, and you'll see it, the atomic numbers are all the same. It's still carbon, but we have different masses. Okay, so they each weigh a different atomic mass. We won't worry about that too much. It's just so you're aware that isotopes do exist in nature. The way they look at that is that they take an average of the isotope atomic masses, and that's what you see on the periodic table. But all in all, typically isotopes exist primarily in one state. Okay, so for carbon, it's our carbon-12 isotope. These three do exist. We rarely have to use them. Okay, it's just to show you where those actually come from. Okay, so I'm going to touch then briefly on electronic configuration. Okay, so now we're looking at our electrons here. So we've discussed our atomic number. That's our number of protons in the nucleus of an atom. Our mass number is our protons plus our neutrons. But we do represent atoms using our electronic configuration. So what this basically highlights, okay, is that I was talking about the electrons, so I'm going to go back very briefly here. So this is a basic diagram of an atom, okay? So our electrons, depending on how much our atom has, are flying around in this electron cloud surrounding the nucleus, okay? That can be incredibly hard to interpret, depending. So if I were to show you this diagram, it'd be very hard to interpret how many electrons this atom actually has. So how we represent that and the number of electrons it has is called the electronic configuration. Okay. So taking this example, okay, so we have aluminium. We have an atomic number of 13, which means we have 13 protons in our aluminium. And we have a 27 atomic mass unit. Okay, so this is our mass number, our number of protons, and our neutrons. If I were to then demonstrate how these electrons would be represented then. So we'd represent the shells that these electrons are on by drawing, we have our nucleus, we have our first energy level, our second energy level, our third energy level, and so on. Okay. So how many, just as a kind of quick question, how many electrons do you think aluminium has?
13.
13, exactly. Okay, because like I said, it's a neutral atom. We have 13 protons. We don't have any additional charge, so we must have 13 electrons to cancel that out. So how we represent that then is that we take our first energy level here. Okay, so this is normally the first circle surrounding our nucleus. And that can hold a max of 2 electrons. Okay, so that energy level is very, very stable with just having 2 electrons in it. Okay. We then move on to the second energy level, and our second energy level can hold a max of 8 electrons. Okay, the first energy level can only hold 2. To be considered stable, the second energy level can hold up to 8 electrons. Okay, so at a max of 8 electrons, no more. So that's what's represented here. Okay, so you see our first 2 electrons on the first energy level. We move on to the second energy level, and this can hold our third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th electron of aluminium. Okay. And then you'll see on the third energy level, then we have our last 3 electrons to take into account is our 1, 2, and our 3. And that completes our electronic configuration then for aluminium. Okay. What you need to take from this is that, and this is quite important, that the first energy level can only hold 2 electrons. Once you move on to the second energy level, that can hold 8 electrons. The third energy level can hold a maximum of 8 electrons, and so on and so forth. What we need to be able to do by the end of the course is that you should be able to write the electronic configuration for the first, we're going to say 29 elements. More often than not, it's the first 20. Okay, so we'll do practice on those over the course of the semester, but by the end of it, you should be able to write the electronic configuration for the first 29 elements. Okay. So I'll show you briefly then what that looks like. Okay, so this is the first 20 elements. So this is basically just following our periodic table. Okay, so you'll notice for hydrogen, we only have 1 proton. So that means we only have 1 electron to fill in. And that's what you'll see there. Okay. Our helium then, so that's considered quite stable. Okay, so we have our 2 electrons on its first shell. We actually don't need to take into account the second energy level. We can only fill in 2, and that's considered stable. So you may notice, and I kind of touched on this briefly in the first lecture, that I mentioned that our group 1 alkali metals, they're very reactive. Okay. You'll notice why here. Okay, and we won't get into this evening. We'll kind of cover this in maybe next week when we're talking about bonding. But each of these have 1 electron on their outermost shell. So you'll see it there. Okay, so on the most outermost shell it has, you'll see 1 electron. That renders that particular element very reactive. It basically wants to get rid of that outermost electron in order to be stable, okay? Because the next energy level down is stable, okay? So it has a full outer shell. That's exactly how it wants to be. But all in all, it has this 1 electron on the outermost shell, okay? So that's why you see such reactivity with these elements, is because it's looking to get rid of that outermost electron. Spinning back over here then to your noble gases, okay? So your helium, neon, argon. These have complete stable outermost shells. Okay, so you'll notice there our helium has 2. It can only fill in 2. Neon there has 8 on its outermost shell. That's the way it loves it. It wants to be stable. And argon then has another complete 8 shell there, 8 electron shell. So these are why these are stable, whereas your group 1 elements are highly reactive. Okay. Is everyone happy enough with that? So far,
Yeah.
Sorry, you see for potassium and calcium,
yes.
does the position of the electrons matter? See, you see they're all kind of top, bottom, left, and right, but for those 2, some of them are kind of coming off diagonally.
Oh, I see what you mean. I think this is actually, no, that doesn't, they're normally drawn like this. I think that is literally just trying to fit that diagram.
That's what I was, okay, that's fine.
Yeah.
I just wanted to make sure it didn't go a bit mad towards the end.
No, not at all. Like this kind of, these are kind of simple diagrams of these elements. Okay, so what you typically do is kind of create 2 electrons in pairs, similar to what you'd see with like sodium, magnesium, and so on. This is just kind of a squish diagram.
Oh, okay, perfect. Thank you.
Okay, so that kind of brings me to the end of the lecture notes anyway. Okay, so what I'm planning on doing now is that I've uploaded a worksheet to Moodle. Okay, so you should see it in the folder where your lecture notes were. I've uploaded that. If you want to take maybe 5-10 minutes just to review those questions, and then what we'll do is for the last maybe 20 minutes of the lecture, I'll go through each one of those and we'll kind of correct them as we go. Is everyone happy enough with that?
Yeah, perfect. Thanks.
I actually don't have access to Moodle yet, so I can't see the worksheet.
Okay, no problem. What I can do is I can share the screen that I have and
Okay.
Okay, so you should be able to see that there now. Is that okay?
Yeah, great, thank you.
No worries at all. So I'll give you about maybe 5-10 minutes just to kind of look over that and then we'll go through it ourselves then. Okay, perfect. So I'm looking at this worksheet 1 there. Okay, so it says circle the elements in the following list. So does anyone want to call out what they got for that one, or you can fill in the poll, it's no problem.
Yeah, MG, PB, and AR.
Mg, Pp, AR. Perfect. So you're just missing one of them. Okay. So you're correct in saying that magnesium, your Pb, and your AR, they're all correct. Oxygen is also an element, okay? Because if you were to look at oxygen, if you were to divide that simply, you would still have the same atom, okay? So that, by definition, is your element, okay?
Okay.
So the reason the other ones aren't, so your MgSO4, your HCl, your H2O, your water, and NaCl, is because they're composed of two or more atoms of different atoms, okay? Your oxygen is the same atom. The other compounds that are shown there are compounds of the same of two different atoms. All right.
Okay.
So the correct answer you should have here is you're right in saying your magnesium, your lead, so your Pb, your argon, your AR, and then your O2. So moving on then to question 2 then. So define a liquid in terms of shape, volume, and compressibility. Would anyone like to call out their answer for that one?
Second one.
What was that, sorry?
No, I don't know.
Yeah,
I
that's
think
no problem.
second one.
Yeah, so for question 2.
Yeah. So
Yeah, it's no problem. So what we should be saying here, so define the liquid in terms of shape, volume, and compressibility. This is what I was talking about in regards the states of matter. Okay?
yeah.
So a liquid will assume the shape of the container it's in. Okay, so not like a solid, it doesn't have that kind of rigid fixed arrangement of particles. The particles are more free flowing. Okay, so they do interact with each other, but they have space to move around and flow against one another. Liquids do have a definitive volume, okay? So they assume the shape of the container they're in, but we can measure their volume, okay? So we can pour out a sample of a liquid and determine its volume based on graduated gravimetric, okay? Compressibility then, so liquids can't be compressed because if we were to compare that to a gas, so in a gas, it's more chaotic. All of the particles in gas are moving around very, very quickly. There's a lot of space between the particles. They have very little interaction between them. Our liquids, they do interact. So there's not very little space, but there is little space to allow for compression of a liquid. Okay. So just to recap then, so question 2, in terms of shape, it assumes the shape of whatever container it's in. The volume, it does have a definitive volume that we can measure using graduated cylinders, burettes, and pipettes. And the compressibility, as they show little to no compression because there's little space surrounding each of the particles in a liquid. Okay? Perfect. Is everyone happy enough with that then? All good so far. Okay, so then on to our question 2 then, okay? Or sorry, it's question 3. So it says describe the following as a physical or chemical change. All right. So I did put up on the poll here, so which of these are a chemical change? So your chemical changes there are part B and your part C or part D, okay? So the reason part B is a chemical change is because we're heating mercury oxide, okay? So we're applying heat in order to decompose mercury into 2 different substances, your oxygen and your mercury element, okay? This is changing the substance, so that is a chemical change. Part D then, so in a very similar way, we're igniting a strip of magnesium. So we're deliberately reacting magnesium with oxygen in the presence of a flame, and we're forming magnesium oxide. So we're forming a different product, therefore we have magnesium has undergone a chemical change. So I'm not sure who, it doesn't matter, but so your first one is sodium chloride is obtained from seawater by evaporation. So this is a physical change, okay? Sodium chloride in the water, when it's in liquid form, sodium chloride is present in the water. It's still there, it retains its sodium chloride. When we evaporate off the water, sodium chloride doesn't change, okay? So sodium chloride itself doesn't undergo a chemical reaction. we're simply removing the water from sodium chloride. Okay, so the sodium chloride that's in the water and what we end up with after evaporation is the very same. It doesn't undergo a chemical change. The same for part C. Okay, so we have pure ethanol is separated from an aqueous solution by distillation. So distillation is basically heating a mixture, an aqueous mixture, to certain temperatures in order to drive off certain portions of that liquid and then recondense them to kind of purify that liquid mixture. Okay, won't go too much into that. But if we heat that mixture, say, up to the boiling point of ethanol, we'll have ethanol vapor that will rise, go down the cooled condensing flask of the distillation apparatus, and then we can collect it as a liquid itself. But ethanol in that process has not changed. Okay, we start off with ethanol in the mixture, we increase the temperature to change it into its gaseous form. That condenses back in the distillation apparatus, and then we recollect it then as a liquid. So ethanol itself has not changed, therefore it's a physical change. Is that okay with everyone? We can see where I'm getting that from. Okay, perfect. So then part 4 then, so we have list 3 intrinsic properties of matter. So this is what I mentioned earlier. Okay, so this is independent of the amount of substance that we have. So 3 intrinsic properties could be something like its solubility, its color, or its boiling point. Okay, so no matter how much of a substance I have, those 3 properties in particular will not change regardless of how much of that substance I have. So like I said, 10 ml of water will boil at the exact same temperature as 100 ml of water will. The color of sodium chloride, whether I have 5 grams or 15 grams, won't change, and so on. Okay, so these are the properties that will not change or are not dependent on the amount of a substance that I have. Okay, so moving on to part 5 then. So this is just filling out the following table. Okay, so we have our electron, our proton, and our neutron. So what we should have here is that electrons are in that they're in that space around the nucleus. Okay, so they're in that region of space that surrounds the nucleus in the energy levels. The proton then should be within the nucleus of the atom, and the neutron is the same. It should be within the nucleus of an atom. Okay, so the only one that's different here is that the electrons are in that region of space surrounding the nucleus. All right. Moving on to charge then. So what you should have gotten here is that the electron has a negative charge. So we give this a -1. Protons then are positively charged, so that's a +1. And then your neutron then have no charge, so they're neutral. And then finally then for relative mass, so electrons, you don't need to remember the specific atomic mass unit of the electrons. We can just say Na, or they have negligible mass. All right. The only 2 that do count are your protons and your neutrons, and they have an approximate mass of 1 atomic mass unit. Okay. Okay, so moving on then to part 6. So just I threw up a poll here. So what we should have here then is your referencing back to your periodic table of elements. Okay, so we're going to go through the protons, neutrons, and electrons for each one of these. So does anyone want to call out then what they got for iron? Any takers?
I said 26 protons and electrons, but I don't know how to get. I don't know how to see how many neutrons there'd be.
Okay, not a problem. So I can show you this here now. I'll actually go back to our lecture to show you this. Just bear with me 2 seconds. Can you guys see the presentation again?
Yeah.
Perfect.
Yeah.
Okay. So just a little bit of a recap then. So recall that the mass number, all right, so you worked out your atomic number and your number of electrons correctly, okay? Your mass number takes into account your number of protons and your neutrons, okay? So this is a combination of the two. So with that in mind, and if I were to show you aluminium as an example, aluminium has 13 protons, all right? If I know it has 13 protons and then our mass number up above is a combination of our protons and our neutrons, all you do is take the atomic number away from the mass number. Okay? So for that example, what you should have gotten for number of neutrons is 14. Can you see where I'm getting that from, yeah?
Yeah, just when I look up periodic tables, it's only giving me one of those numbers, the atomic number.
Oh, I see. Yeah,
Unless
there are some periodic table of elements that will only show you the atomic number. What I'll do is
okay,
I'll
right.
put up. What I'll do is just so you have it on Moodle, I'll give you an example that has.
Okay, yeah, perfect. Thanks.
Sometimes it's just going to simplify down again just to show you atomic numbers, but we're going to need both of them. All right, but just as a pure example, that's how you would calculate it.
Yeah.
Okay. So if I were to go, sorry, now I'll just start resharing this again. Sorry, now just bear with me 2 seconds. Okay. So for iron then, okay, so can you just remind me what you said for iron?
26 protons and electrons.
Okay, so the mass number of iron is 55, okay?
Huh?
So taking our 26 protons away from our mass number 55, so we should have 29 neutrons there. All right? Can everyone see where I'm getting that from?
Yeah.
Perfect. So just what I'll do is just after this lecture, I will put up an example of periodic table that has both. So you will be able to see where I'm getting those from. But just to note that if you want to calculate the number of neutrons, all you have to do is take the atomic number, which is a smaller number, away from your mass number. All right. I'll do one more example of that then. So say for your calcium, okay, so if we were to look at the periodic table of elements for calcium, we'll see an atomic number of 20, okay? So what that tells me right away is that I have 20 protons and I have 20 electrons. Calcium has a mass number of 40. So if I have 20 protons, I know there's 20 protons within that 40 mass number. I just take one from the other and I should have 20 neutrons as well. All right. Just one more example then. So just looking at our chlorine. Okay. So chlorine then, so that has an atomic number of 17. So again, 17 protons, 17 electrons. Chlorine has a mass number of 35. So just taking our 17 protons away from that total proton and neutron number of 35, we should have 18 neutrons there. All right.
Mm-hmm.
Perfect. Okay. And then last but not least then, so we have what you understand by the term isotope. Okay, so isotopes, they have the exact same atomic number. So they're elements that have all of the same atoms. Those atoms all have the same atomic number, but they differ in mass number. Okay.
Mhm.
So they're still the exact same element. If you were to split those down into its simplest form, we still have our atoms that have the same atomic number in each one, but they have different mass numbers, which means they basically have different numbers of neutrons. All right. So we probably won't do an awful lot of work with isotopes. We'll more focus on the kind of more abundant isotope in nature, so like our carbon that I discussed earlier. But it's just good to note that you know the definition of an isotope and where they actually come from. Okay, is everyone okay with that? So
Yep.
perfect. So I'm going to stop sharing my screen now and I'll pause.